Of the sign convention. If you have a beam like this and you have two moments like this, and they are going to bend the moments so that they make a smiley face, you have the positive moment. Here the upper part of the beam is under compression and the lower part is under tension, and pay attention to these shear forces. If this part is upwards and this part is downwards, we have positive shear. On the other hand, if a beam is going to be bent like this, it is going to, for example, making a sad face, you have minus moment. In this situation, the upper part is under tension and the lower part is under compression. And you can see that this is the negative shear. So in question 3-4, first of all, let me do the calculations. Let's first of all plot the free body diagram of the beam. Here is point A and point B. At this point we have RAY and RAX, but at point B we just have RBY, and there is a distributed force in here and the magnitude is 6 kilonewtons per meter. So I'm gonna calculate the reaction forces. First of all, the equilibrium equation in x direction, just like the previous two problems, gives us the RAX equals to 0. Then I have the sigma m at point B equals 0 at this point. So, and this direction is marked as positive. So RAY times this distance, which is, here is 2 and here is 8. So RAY times 10 minus the moment created by this distributed force. Again, we are going to substitute it with a single concentrated force of 6 times this distance, which is 8. At the middle of it, here is 4 and here is 4 too. So the moment it creates is equal to 6 times 8 times 4, and it is equal to 0. This gives us RAY equals to 19.2 kilonewtons, and it is upwards. So in the last equation, we're going to write the equilibrium equation in y direction with upwards as positive. So here we have RAY minus the distributed force 6 times 8 plus RBY equals to 0. This gives us RBY equals to 28.8 kilonewtons upwards. Okay. To plot the diagrams, I'm going to plot the beam again, because it is always better to draw the diagrams just underneath the free body diagram of the beam. So here I have a 19.2 kilonewtons force, and this distance is 2. From this distance until the other end of the beam, I have this distributed force of 6 kilonewtons per meter, and here we have a RBY of 28.8 kilonewtons. Okay. For the shear force, we're going to start. Just remember that you have to pay attention to all the critical points. Here, the critical points is this point, point A, this point where the distributed force starts, I'm going to name it, say C, and this end, which is B. So, here, if you just cut the beam a very small distance, you can see that here you have upwards shear and here you have a downwards internal force. So based on the sign convention, you have positive shear. So here we're going to go up to 19.2 and we have a positive shear until point C. From point C, we have a distributed force of 6 kilonewtons per meter. It means that for every meter you go ahead, you're going to subtract 6 kilonewtons from this initial shear at point C. So you're going to gradually decrease it until point B, that you have the negative shear. Why negative? Because if you cut beam from this part, you can see that here you have a upward shear and here you have downwards. So based on the sign convention, it is negative shear. So at this part, you have negative shear of 28.8 kilonewtons, and from point C until point B, you are going to linearly decrease the shear force. This is the shear diagram of the beam. You can see that here, at this point, zero shear situation occurs. So it can also be considered as a critical point. If I name this distance X, I'm interested to calculate this X. As I said, this 6 kilonewtons per meter means that for each meter you go ahead to the right hand side, you're going to decrease this shear for 6 kilonewtons. So at this point, I'm going to name it D, M, V at D, the point D is 19.2 minus 6 times X, and it is obviously equal to 0. So from here, X is found to be 3.2 meters. And it is a critical point, obviously. So we're going to plot the bending moment diagram. It is obvious that at the two ends of the beam, bending moment is equal to 0. So we have 0 here and here. And at point C, we have a critical point. At point D, we also have another critical point. So from point A to point C, we just have this shear force. So the bending moment will be linear. At point C, the moment equals to 19.2 times 2, which is 38.4 kilonewtons per meter. So this is 38.4. Here you can see that at this point D, that we have zero shear situation. It means that the slope of the moment diagram is 0. So somewhere here we have the 0 slope, and we're going to here this point, and after that we're going to go to 0. So it is going to be something like this. And if you're interested to calculate the value here, for example, M at point D, we have 19.2 times 5.2, because this distance is 2 and this x was 3.2. So, and you also have to calculate the bending moment as a result of this distributed force. You can see that we are allowed to substitute it with a concentrated force, which has the magnitude of 6 times 3.2 at the middle of this x. So this is 1.6, and the bending moment as a result of this distributed force here is equal to 6 times 3.2 times 1.6, which is totally equal to 69.12 kilonewtons per meter. Here is 69.12, and here is the bending moment.